So yeah, let's get started. Okay, so if you don't know me, my name is John. Ryan's like, oh, thank you, Carol. Ryan's on vacation in the Black Forest right now. So I will be teaching today, and what I'm going to be talking about is the subject of the unique games conjecture and how it relates to dictator testing. So you should set your mind back to a week ago, skip over the last lecture we had, because this goes back to some older material. So what is the problem of unique games? What is this problem? It's parameterized by a number positive integer q, and we say the unique games problem, it's a constraint satisfaction problem. Games q. Is that about good for you?
Yeah, that should be all right.
Okay. Is this the constraint satisfaction problem with two properties? One, okay, so what are the labels? The label set will be the set of integers from 1 to q, which you write with this boxy notation. And you have a set of constraints that you're allowed to place on variables, pairs of variables. So you're allowed to place all two-variable so-called bijective constraints. Are allowed. Okay, and we haven't actually defined what bijective constraints mean, but so I'll do that now. Basically, if you have two variables u and v, and they appear in your variable set, then you can place a constraint which says that the label you give to v, so the label you give to v, so if f is a labeling, then it says that f of v, then there's some bijection pi, where when you apply pi to f of v, you want that to equal the label that you give to u. Okay, so where f is a labeling and pi is a bijection. Okay, so that's the overview of the problem. Basically, I'll just draw a little picture. I know everyone here knows what a bijection is, but I'll pretend like you don't. So you have variable u and v, so u's labels, and you can write out v's labels. And they come from this set of q different labels that you can give, 1 to q. And similarly for v's labels. And so there's this permutation pi that says, or this bijection pi that says you map 1 maybe to 2, maybe 2 back to 1, and q somewhere over here, and so on. So there's this matching on the graph. And the constraint says that for me to satisfy this constraint, which you represent with this thing, it must be the case that whatever label you give to u and whatever label you give to v, there's one of these edges that connect them. Okay? And so this kind of makes it somewhat clear why this thing is called unique games. I won't go into the whole name, but at least the unique game, or the unique part of it, makes some sense, which is that any label that you give to u uniquely determines the label you must give to v to satisfy this constraint, and vice versa. If I give you a label for v, I'm constrained in what I must give to you uniquely. Okay, so that's the unique games problem. And there's a more common way to represent instances of this problem that makes something that was implicit in that definition very explicit. And so we're going to be focusing on this version of the definitions, which is an instance of the unique games problem, which we'll name with g. G of UGQ is, well, you have, again, the variable set. And we'll write that as capital V. And then you're given a graph over the variable set. So a graph G equals V. And I've used the same G for like the name of the instance and also the name of the graph. So you should kind of like associate this graph with the instance. Okay, they're basically the same thing. And so, you know, it's a graph that looks maybe something like this. Here you have five vertices. So my unique games instance has 5 variables in it. And I draw an edge between 2 variables if they appear in some constraint together. Okay, so if this is variable u, this is variable v, then there's some constraint that they fall in together. Maybe that corresponds to the bijection pi. And then let's say this is edge E. So a labeling satisfies the edge. Satisfies E. And labeling F satisfies this edge E. If, you know, the obvious thing happens, if when you do f of v and apply the bijection to it, you get out f of u. Okay, so that's just a slightly different way of looking at the problem with graphs. Okay, so this is kind of like an abstract definition. So what is a concrete example of the unique games problem? And the most common example, almost any time you ever see unique games, you're going to see this one example. It's called 2ln mod q. And it corresponds to the problem where you're given some 2 variable linear equations modulo q. And they all look like this. So you're going to have variable 1 minus variable 2 equivalent to some number, mod q. And you're given a big set of these. Okay, so 2 variable linear equations mod q, all of the form like variable 1 minus variable 2 equals a number. It's pretty easy to see that all of these are can be equivalently stated as bijective constraints, simply because, you know, for example, in this first equation, whatever I give to x2, like let's say I give it the value 5, I label it with the value 5, then I must give x1 the value 7 to satisfy this constraint. So whatever, for any given constraint, if I label one of the variables, my hands are tied, and I must label the other variable to satisfy it. And just to link this back to that thing, so this corresponds to the graph where you have these variables x1, x2, and so on. So those are all the vertices. And maybe this is variable x1 and x2. So they both fall in this first constraint. So they have an edge between them. And then they're labeled with the permutation pi. And that pi, in this case, just says whatever value I assign to x2, I must give that plus 2 to x1 if I want to satisfy that. Okay? So yeah, that's a definition and an example of unique games. Any questions about that? Is there an eraser here? Is this an eraser? That is not an eraser. Anyone seen an eraser, like lying on the ground or something? I guess I can use my hand.
Oh.
Huh?
Is that a chalkboard eraser on the projector?
Oh, this Steely?
Oh, actually.
Does this look like something I can erase? Yes. Okay. Awesome. Thank you. Man, things are looking pretty bad there for a second. All right. Yeah, I'll erase a little more. Just for fun. Okay. So what is known about the unique games problem? So I'll start with a fact. This is going to be a fact. What is known, you know, you're given this unique games instance, you want to satisfy as many things as possible. So what do we know about how hard it is to approximate unique games? So it turns out that the problem of 1, 1 approximating unique games is actually easy. And what is this? This is, again, if you don't remember, the problem where you're given this unique games instance, and someone tells you that there's an assignment that simultaneously satisfies all of the constraints, And it's your job just to find such an assignment. Okay, so why is this problem easy? Well, let's say you took that optimal assignment that satisfies everything, you just kind of fix that in your mind. If someone came up, for example, in this graph, if someone came up and just told you the label that that assignment gives to V, maybe not the rest of the graph, maybe just V, then I claim that you can actually find the rest of the assignment as follows. So if I know the label V, then because there's like a bijective constraint on this edge from V to U, if I want to satisfy this edge, there's one thing that I can label U with and nothing else. So in this labeling, I know what U has to be since I know V. And similarly, because I know U, I know all of U's neighbors, the labels that are given to those neighbors, simply because all of these edges are bijective as well. And so I can kind of propagate this labeling for V out to the rest of the graph and regain the original labeling for the whole thing. And okay, so that works if someone gives me the label of V in this optimal labeling. But if someone doesn't give that to you, it's still not a problem because, there are only Q things you have to try for the label of V. So if you just try all Q of them, then in polynomial time, you'll be able to recover the optimal solution. Okay? So it's a pretty simple algorithm, and that approximation problem is easy. On the other hand, the unique games conjecture says something else. It says that if you're given an instance of unique games in which you can't satisfy everything at once, you can satisfy maybe 99% of the constraints simultaneously, then the problem goes from being easy to like extraordinarily hard. Okay? And so in like a mathy language, that's stated as follows. So for any small constant you want delta, you can take this parameter q as large as you want. There exists to make the problem as hard as you want, such that delta, 1 minus delta approximating. Okay. So in other words, you should think of delta here as like 0.01 or something like that. In which case this says, if I have this parameter q, so the label set, large enough, then it's the case that if someone gives me a 99% satisfiable unique games instance, so there is a solution that satisfies 99% of these bijective constraints, then it's NP hard for me to find even something that satisfies 1% of those constraints. And instead of 1%, you can make that even harder, like 0.01 or whatever you want. Okay, so this is a unique games conjecture, and as Ryan has kind of alluded to, it's somewhat controversial, and like not just between people, but like within an individual person, because like no one really has a strong feeling of whether this should be true or false. I'll just state a couple things, which is that there's this other problem called label cover that looks somewhat like this. It was kind of the inspiration for this unique games conjecture. And for this problem, label cover, we actually know that it is this hard to approximate it. So, there's a similar problem that's just as hard as what we would like this to be. So, that's kind of evidence in favor of the unique games conjecture. On the other hand, there's this recent algorithm of Aurora-Barak-Steuer, which actually solves the unique games conjecture, but in like sub-exponential time. So it's not awful, it's not exponential time, but it's not polynomial time. So some people took that as like evidence that maybe this conjecture is false. My own belief, which you probably don't care about, is that, I don't know, I like to think it's true, because if you assume it's true, like a lot of nice things happen. So I like this conjecture. Now I'll just give one theorem. What is known about the hardness of, we'd like to prove this, but we can't, so what can we prove? And the state of the art currently is NP hard to, well, instead of delta and 1 minus delta, we know it's NP hard to 3/8 and 1/2 approximate this problem. Okay. So it's NP hard if someone gives you a half satisfiable solution to find a satisfying assignment that satisfies at least 3/8 of the constraints. So ideally, what we'd like to prove is we'd like to get this 1/2 as close to 1 as possible, and this 3/8 as close to 0 as possible. That's like the dream world. And as you can see, we're kind of far away from that. Okay, so that's what we know about unique games. Now, like I said earlier, if you assume this unique games conjecture, you get all sorts of really nice things. So what I'm going to prove to you guys in this class is one of those nice things that you get out of this, which is you get a very nice and explicit correspondence between these dictator tests that Ryan has been talking about and hardness results. So the next two things I'm going to write like a theorem and a definition. They're somewhat of a mouthful, so let's just jump right into it. So this theorem basically says if you get if you have a dictator test and you assume the unique games conjecture, if you have a dictator test that uses some predicates, then you automatically get an NP hardness result for those predicates, for approximating those predicates with exactly the same parameters as your dictator test. Okay, so the theorem is that if you give me a constraint satisfaction problem with a domain that's Boolean, and has some predicate set with what we're going to call psi. And then if you also have a dictator versus no notables test that uses psi, which we're going to call that test T, using psi. Then you get the hardness result. For all delta greater than 0, it is so-called UG-hard to approximate this problem with these parameters, alpha plus delta and beta minus delta. Approximate. Okay. So in words, you fix a CSP with a Boolean domain and a predicate set psi, and if you have an alpha beta dictator versus no notables test T that uses psi, then it's UG-hard to alpha plus delta, beta minus delta approximate the constraint satisfaction problem that uses these psi constraints. And that's for all delta. Okay? So just a couple of remarks. I'm going to prove this for the case when you have domain Boolean. This is actually true as well if you replace that by any finite domain. It's just a heck of a lot easier to prove it in class when all you have is -1 and 1 to deal with. Okay, so that's the first thing. And the other thing is, as Ryan mentioned, this delta is somewhat of an irritant because, or at least in some cases, because for example, if your beta here is 1, which is a very nice number, as opposed to 1 minus delta, if it's actually 1, then you're going to go from 1 to 99% there, which is sometimes not optimal. And oh yeah, so what does it mean UG-hard? That means if you assume the unique games conjecture, then it's NP-hard. Okay, so any questions about the theorem? Okay, if not, Carol, you look shocked. Oh, awesome. Yeah, it's a pretty cool result.
Are you going to show a reduction?
I will show a reduction, yes. From the unique games problem? Which you assume with these parameters it's NP hard to solve. And I'm going to reduce from that to this max CSP with psi constraints. Okay. So before we do that, I assume you've maybe forgotten a little bit what this dictator versus no notables test definition is. It's kind of like a monstrous definition. So I'm going to recall the more salient aspects of it. So an alpha beta dictator versus no notables test. It's what Ryan called a local tester for functions f, functions of the type f which receive Boolean inputs and output into Boolean values, which satisfies a couple properties. So the first one is you want dictators to pass with high probability. So if f is a dictator, then it passes with probability at least beta. Passes. And the other one is that if f is far from a dictator, then you want it to pass with low probability. And what was our notion for being far from a dictator? It just meant that it has no epsilon epsilon notable coordinates. So if f has no then it passes with probability at most alpha. Plus some like this weirdo lambda of epsilon error term that's kind of a nuisance, but is always with you. Okay, and if you remember this thing, I'm not going to really write it out, but this was something which, as epsilon goes to 0, this also goes to 0. So for small epsilons, it's something that you really don't have to worry about. Okay, and then let me just say what this meant again. This means that the ith influence on f, at least if you care about this 1 minus epsilon noisy version of it, is at most epsilon for all I. Okay, is that correct? Yeah. Okay. So yeah, that's a definition of the dictator versus non-notables test. Only it actually isn't the definition that we're going to use here, because there's one thing wrong about it for our applications. You probably remember Ryan, like a week ago, doing something like this, saying, "Oh, well, you know, we don't actually want to prove it for -1, 1. We actually, for some weird reason, need it for the interval -1, 1." And he was like, "I'm not going to say anything about it because I don't want to say anything about it because it's like really annoying." And in doing that, he made it so I had to say something about it. So that's going to be the next little board. So what does it mean to test functions that map into this interval -1, 1 instead of functions that just map into the set -1 or 1? And so what I would like to tell you is that it's easiest to view such functions as like randomized functions in a pretty obvious way. Okay. So if we think of some input x, some Boolean input x, we evaluate f on that Boolean input, then we have that f of x is going to equal some value mu, which lies in the range -1, 1. And there are a couple easy cases, like how should we interpret these values? If mu is either -1 or 1, then that's actually good, because it's like f has made up its mind. It knows it wants to be at one extreme or the other extreme. And similarly, if mu is 0, then kind of f is as random as you could think about it, because it's totally on the fence regarding whether it wants to be -1 or 1. And so, you know, the most natural probability distribution to associate with that is just the uniform distribution on the two elements. So more generally, we're just going to think of this function as the probability distribution on the set minus 1, 1 with mean mu. Okay? Okay, so that still doesn't say what it means to like test such functions, but at least we know these functions, there's a natural way to interpret them as probability distributions. Okay, so let's say we have a function tester t, and let's say it tests a certain constraint. So how do these function testers work? Well, you know, they're already R function testers. They query R points. So the first thing it does is it selects x1 through xr. And then it queries the value of f on these points. And then it checks whether the R values it gets from f satisfy some constraint psi, or whether they don't. Okay, so that's like, this is a form of a generic test that such a tester might use. And, you know, this, in our normal case, this makes sense because we know that the psi that we're looking at takes in Boolean inputs, R of them, and outputs into 0, 1. Okay. But in this case, we're looking at f's that have that output into the interval minus 1, 1. So how do we interpret this? Well, what we should think of is each of these guys are probability distributions. So this thing that I've written here corresponds to what you get if you first draw R values independently from these R probability distributions, and then take the expectation of this psi function as you plug those values in. So let me write that out. That's just equal to the expectation if you sample B1 from the probability distribution f of x1 down to BR from f of x to the R, and you test psi of B1 through BR. Okay. And so this value now, whereas psi used to be outputting either a 0 or 1, when you input things that are map into the range minus 1, 1, the psi will output something in the range 0, 1. It's an expectation. Okay.
Did you say that distributions of x1 to xr need to be independent?
Yeah. Yeah.
Like Carnegie doesn't have some joint distribution to choose odd points?
So what I actually think of is no, so this is like how I define what it means to test this.
Okay.
So like, you know, usually you query a function at a point, and it will give you like a minus 1, 1 value. This is what happens if you query that function at a point, and instead of giving you a minus 1, 1, or instead of giving you its value at that point, it then uses this probability distribution to just sample one for you. So you can almost think of it as like you don't have access to the function, you have access to like the outputs of its probability distributions. So yeah, that's what it means to test functions that output into that interval. And really all you have to think about is, all you have to remember for this lecture is like these 4 lines or whatever. Because there will be one point where I will use them. Yes, Misha?
So we have this test result which is a number from 0 to 1.
Yeah.
But we want it to first say that f passes the test.
Yeah.
What does that mean?
So, you know, typically you say, when psi was like a 0, 1 valued, the probability that f passes was what? It was just the expected value of psi of like f of x1 down to f of x to the r. So that was an old way to define the probability that you pass a test. And actually, you know, this definition still holds. Because if you take an expectation I mean, you're taking this expectation of something that's now between 0 and 1, you still get a number between 0 and 1. Okay, does that make sense? Cool. Okay. Yeah, so unless anyone has any questions, any other questions, I'm going to begin with the somewhat lengthy proof of this theorem. Okay. Okay, so as Ankit asked, like, how do we prove this thing? We do it by a reduction. So hopefully you've all seen reductions before. It's going to be of the following form. We're going to construct some method of transforming unique games instances, which we give the name G, into max CSP instances. Which we will give the name P. And what we want for this to work is that if we want a couple properties. If our unique games instance has a high optimal value, so if we're in the case when the optimal value is at least 1 minus delta, then it should be the case that we can also get a high value for the max CSP instance. Max opt of P. And what value are we shooting for? Well, we're shooting for this beta. You remember beta here is like bigger than alpha. So we're going to want something that's like beta, and then eventually we're going to get minus something small. And the other property we want is that if my unique games instance has a very small value, like less than or equal to this delta, then the optimum value of the max CSP instance is itself small. Yeah, another way of stating that is in the contrapositive, which is that if the optimum value of P is large, so it's greater than or equal to something, which I'll fill in a second. Well, I can fill in the beginning. It's going to be, if it's bigger than this alpha plus some other stuff, then that means the optimum of your unique games instance, G, should be strictly bigger than delta. Okay, and so yeah, so this says that the only case when you ever get, well, every time your optimum of G is large, then you'll get a large optimum of P. And similarly, the only case whenever you get an optimum of P that's large is when your unique games instance has a large optimum. There's one other thing, which is that we want this to be polytime computable in polynomial time. And this is all I'm going to say about it, because if you stare at what we do, or what I'm going to be doing for the next 50 minutes, you'll see that indeed it is polytime computable.
John, that epsilon in your
which epsilon?
G versus NN test definition, I do not recall.
This epsilon.
Yeah. Is that a parameter up there, like alpha, beta, epsilon? I'm not sure. How is it?
No, so I think this is for all epsilon. Your test works like this. So like, you give me a test, and then the smaller I make epsilon, if I make f have less and less notable coordinates, then it's guaranteed to pass with lower and lower probability. Okay.
No, but beta and alpha are fixed, right?
Oh yeah, they're definitely fixed. Yeah, it'd kind of be weird to have like here 2 things that depend on epsilon, because why not just use 1? Okay, and well, actually, I'll fill in this blank right here. We have that epsilon over there that corresponds to like how well the test does on functions without notable coordinates. So what we're actually going to prove is that if you fix some epsilon, then this P satisfies if this optimum value is at least alpha plus 2 times lambda of epsilon. so it's 2 times lambda of epsilon larger than what you want it to be, then what you can actually prove is that this is at most, this is what we're going to do, big O of lambda epsilon times epsilon to the 5th. Okay? And so what we're going to do then is set this. We're going to choose the delta in our unique games instance to be smaller than this. And then on this side, we're going to get a big O of delta here. It's not too important. If you just look at the bigger picture, which is, you get a small value here, if and only if you get a small value there, then that basically presents an accurate impression of the proof. Okay. Oh, one more thing. We can assume that G is regular. I won't say why. There's like some paper that shows that whenever you do any of these reductions, you might as well assume G is regular. And so I will. Okay, and why is it good that G is regular? Well, if you have a regular graph and those correspond to the constraints in your unique games instance, then that means that all the variables, each variable is in just as many constraints as every other variable. Okay, so let's start with this then. It's going to be a little while before I say what the full reduction is, but at least I can say, starting from this graph, G equals VE, I can say what variable set we construct for this max CSP instance. And that variable set is the following. P has a variable set V cross minus 1, 1 to the Q. In other words, for every vertex of my unique games instance, I introduce a set of hypercube variables for my max CSP instance. And so what is an assignment to P? An assignment just looks like this. It's a function f, which maps V cross minus 1, 1 to the Q into minus 1, 1. But, okay, so you could phrase an assignment as being that way. But, by doing so, you've kind of forgotten where you came from, which is you introduce a separate hypercube for each variable in your unique games instance. So kind of it's easier to think of this as we do the proof. It'll be easier to think of having a separate function for each hypercube. And so equivalently, I could write an assignment as being the function f sub b, which maps minus 1, 1 to the q into minus 1, 1, and just say that I have such a function for each vertex in my unique games instance. Okay. And of course, if someone gave you this, you would just get each of these functions by fixing the variable in the first coordinate. Okay. And what would we like these functions to be? So, like, when you design this instance, you would be infinitely pleased if your functions had a certain form. And as always, when you're designing these things, you always want your functions to be dictators. You don't always get that they're dictators, but you would like them to be dictator functions.
So some motivation for the variable set. So you're getting like, you will have, let's say there are two q's equal to 2, then you will have x 0, 0, 0, 1, or whatever. 0, 1, 1, 0, 1, 1, right?
Yeah.
Okay, why? So what does this stand for?
Oh, I mean, what you should think of is I have my functions. I mean, I introduce like a huge variable set, right? Corresponding to all of the vertices in that hypercube. And I have some function on them. So, if I have this function, it's going to receive q input bits. 1, 2, q, right? So what you should think of is that my function f, if it's a dictator on the ith bit, corresponds to v having the label I in my unique games instance.
No, so which are the variable, let's say, picks up node x, right?
Yeah.
Then you have like x0, 0, 0, 1, 1, 0, 1, 1. So you're saying if it has label 0, then which of these variables should be set to 1?
You should set the variables based off of the dictator assignment.
So which means if it has label 0, then x0, 0, 0, 1, both will be set to 1, and then 1, 0, 1, 1 will be set to
Wait. So,
can you actually take this one?
yeah. So what you're saying is if I have a function f and it receives 4 points, -1, 1, -1, -1, 1, 1, -1, and 1, 1. So this is my function, f, and if like you came from a unique games instance where you wanted to label this function, where you wanted to label vertex v with the label 1, because your vertex set is going to be 1 or 2, then you should make this function to be the dictator corresponding to the first coordinate. So you just get this. Does that make sense? And if you came from a unique games instance where you labeled v with the second label, then that would correspond to making this f of v function the dictator on the second bit. I don't know. We've done similar things before in this class where you take a label and like out of that construct a corresponding dictator function. It's kind of weird every time you see it, but hopefully it makes some sense. So can I?
Yeah.
Okay. Anyway, yeah. So where was I? Okay. So what would we like? Just as I was saying right there, we would like our functions f sub v, when you give it input x, to be equal to a dictator on some bit L sub v. And this L sub v corresponds to a labeling in the unique games instance. Where L is labeling. Okay, so let's see how this works. Again, I haven't told you what the constraints in my instance P are, but at least let's see how this works for the variables. So back in the unique games instance, let's say that for some edge which went from U to V and had a bijective constraint pi on it, so that's edge E, say that L satisfied that edge. E. In other words, how do we define that? Well, we said that if you look at the value that L gives to vertex V and apply the bijective constraint to it, then you get out the value that L assigns to U. Okay? So now in our world of functions, instead of U and V, we have like functions f sub U and f sub V, okay? Corresponding to these two variables, or vertices. So let's draw these functions out, f sub v and f sub u. And, you know, it's going to have all sorts of inputs. And, you know, these correspond to the Q labels of V, and these also correspond to the Q labels of U. And we have this bijective constraint between the labels of V and U. For example, like, maybe your bijective constraint says if you label V with 1, then you should label U with 2. And if you label V with 2, you should label U with 1, and so on. You know, you have arrows, like I drew earlier. Okay. So if L satisfied this edge, so you had this permutation, this bijection was satisfied, then if you make f of v and f of u the corresponding dictator bits, then you get something very nice happening. So for example, if you made f of v the dictator bit corresponding to element q, then we know that because like pi of this dictator bit equals the label of u, that f sub u must be the corresponding dictator bit on the U side. And more generally, even if we don't know like which dictator bits these are, we at least know that if you color in the dictator bit of f of v and then follow the arrow, you'll get the corresponding dictator bit of f of u. This is all remembering that if this is in the case that L satisfies your edge, and then you use that L to assign the f's to be dictators. Okay?
So your edge is not dictator.
Yeah.
Then the edges that you're drawn, I'm not sure. Do they make so? How can you draw the edges between general f and general?
I mean, this is just this edge is all I've done is drawn in that the bijection.
No, but the point is that so this is 2 to the q length vector, right? The one you have drawn.
No, this is q. Because f has q input bits.
No, it's not the truth.
No, this is not. Yeah, this is just this is like if you were to draw out its input coordinates. Okay? And what I'm saying here doesn't make sense if these f's really aren't dictators. I'm just saying keep your mind right now in the case when they're dictators, and let's just like follow what happens. Okay. Okay. So now what I want to say is this is like cool and everything like that, except we have all these arrows and they're like crisscrossing, and it doesn't look as nice as it could. It would be very nice, if all these arrows just went straight down, because that'd make analyzing things easier. Maybe you don't see why right now, but just trust me, and let's see how to fix that. Okay. So what we'd kind of like to do is rearrange the input coordinates of f of v, so that like these arrows all go straight down. What do I mean by that? Well, let's make some definitions. So hopefully you've seen this before, and if not, well, hope you like it. So if you have a permutation pi, just think of pi as being the permutation on this edge, and you have some string x. Define x sub pi to be the string where if I ask for the coordinate, the ith bit of x sub pi, what I get out is x sub pi I. Okay? Yeah, this is kind of weird, but like this means, for example, if I use this permutation that I drew out here, and I ask for the qth bit, so I ask for the qth bit of x sub pi, then the first thing it would do is it would take pi of q and it'd give me q minus 1, and then it would give me x sub q minus 1. So kind of this is a string where first you run all the coordinates to the permutation, and then you output the value. Okay, so that's a function that you can apply to strings, so let's carry it over to functions. So let's define f to the pi to be the function in which f to the pi of x just equals f of x sub pi. So f to the pi is just a function where before actually inputting x, you reorder the coordinates. Okay. And we're still, by the way, now let's remember back to this case where we have these two dictators on like u and v which are connected, and we know that L satisfies this edge. So let's see what happens here. So let's look at f sub v of x when you apply pi to the function. Okay? This will be an exercise in writing down like 20 definitions in a row. So what does this thing equal? Well, by the definition of pi, this is just f of v times f sub v applied to x sub pi. Okay? And remembering back, what is f sub v? It just is a dictator bit on the L sub v coordinate. So this just equals x sub pi applied to the L sub v coordinate. And by the definition of what x sub pi is, this just equals x sub pi of L of v. And remembering that L satisfies this edge, so pi of L of v equals L of u. L pi, x sub L of u. And that just is f sub u of x. Okay. So if U and V, like if you label all of your hypercubes using the dictator assignment of some labeling L, then any two adjacent functions f sub v and f sub u actually will equal each other up to this pi reordering. Okay? Okay. So now with that somewhat weirdo definition out of the way, I can actually define what is the reduction that we'll use. I'll use blue. Okay, so I'm not actually going to give you like all the constraints. I mean, I guess implicitly I will. But what I will give you is a way to randomly sample a constraint from the instance P that we construct. So here's a random procedure for generating a constraint of our max CSP instant. You begin by just choosing a random vertex from your unique games instance. So you choose U and V uniformly at random. Okay? And then, like independently of this, you sample a constraint from your function test, your dictator test. So you draw a random constraint from, let's call the test T. Okay, so again, what does such a constraint look like? Well, you know, it randomly generates R points, x1 through xr. Then it queries the value of f on those points. And then it applies some predicate psi to the R values it gets. Okay, so that's just what the constraint looks like that it samples. Okay. So yeah, pictorially so far, all we've done, we have a vertex U. And now think about it in the unique games graph, it has some neighbors. So even though we picked U, we're going to now shift our focus to U's neighbors. You know, we have R inputs. This is like an arity R constraint, so let's just choose R neighbors. R. And let's call them V1 through VR. And, okay, so you pick some neighbors. Maybe you pick V1 to be this and V2 here. So they come with associated bijections, pi 1 and pi 2. So just let pi 1 through pi r be the associated bijections. Okay, so you've randomly done like 100 different things now. You just have to put it all together. So the constraint that we're going to put on these functions is the following. You basically run the exact same thing that you got out of your tester, but instead of applying it to just some function f, you apply it to these f sub v1, x1 through f sub. So you apply it to the R functions that you get by this random sampling process. And just because, you know, it's nicer to do this, you're going to also not apply it to the actual functions, but like the functions where you reordered the input coordinates to make the functions somehow nicer. Yeah, so it's kind of a lot to see. But basically, one way to think of it is you run whatever dictator test you have. You kind of pick a random coordinate, and then you run the dictator test on like the average of your neighbors. Okay? And one slightly weird thing is that since it's all done independently uniformly, it's certainly possible that you could pick the same neighbor twice, or 3 times, or even r times. Okay, so that's a procedure. Okay, so let's knock off one of the easy cases right now. Suppose your unique games instance has a large optimum value. Okay, so because it has a large optimum value, we know there's a labeling L which achieves this value, or has a value that's at least this. Q have value at least 1 minus delta. Okay. So now I'm going to use this labeling to construct a labeling to my max CSP instance, which passes this random constraint drawn in this manner with high probability. And what labeling am I going to do it? It's just the one that I mentioned earlier. It's going to be the labeling that is the dictator labeling. So for every vertex v, you just set the associated function equal to x sub L of v. Okay. So yeah, now let's think about how well does this do. Okay, so you start by, in this test, you start by choosing a random vertex u, and then you pick r neighbors, okay? Let's focus in on one of those neighbors, neighbor v sub I. So you pick neighbors 1 through r. Let's look at the ith one, where I is between 1 and r. And that comes with its own projection pi I. I claim that on this edge, the probability that L satisfies this edge is actually high. UVI is actually at least 1 minus delta. And why is that? Well, if you remember a long time ago I said you can assume this graph is regular, okay? And so if you know anything about regular graphs, you know that if I sample a random vertex and then a random neighbor of that vertex, I get a uniformly random edge of my graph. And so basically I'm done because I know then, by the definition of value of G, I know that if I sample a uniformly random edge of G, then L, this assignment L will satisfy that edge with high probability, with probability at least 1 minus delta. Okay, so that's proven. But you know, in this way of sampling constraints that I've drawn up here, you don't just satisfy one edge. You don't just sample one edge at once. You kind of satisfy r separate edges simultaneously. So how well do you do on these r edges? Well, for any one of those edges, the probability that L fails to satisfy it is at most delta. Okay? So by the union bound, the probability that L will fail to satisfy at least one of the edges is at most r times delta. Or writing this in a different way, the probability that L satisfies all of them, UVI, for all I in R, is going to be at least 1 minus r times delta, which is, since r is a constant, 1 minus big O of delta. Okay. So what's so nice about this case? Well, you should expect that, you know, if you're basing your assignment on like a dictator labeling of your unique games instance, and if you draw a ton of edges that are all satisfied by the labeling, then your dictator assignment should do well as also, okay? So in this case, well, I kind of erased what I'm going to use. That's unfortunate. But what did I show about dictator labelings when, like, the underlying labeling satisfies the edge? So that's the stuff I did over here, and like I said, I accidentally erased it. But what I showed is that if you take this function f sub v1, where you first reorder the bits, then you actually get lucky, and that equals f sub u. It turns out they're the same functions when you reorder the bits of f sub v1. But this holds for not just the first function that you pick, but all r of them. So this equals f sub v2 to the pi 2, which equals all the way out to f sub vr to pi r. And what does this equal? Well, it just equals all of these guys equal the dictator bit, the L sub uth dictator. Okay. And that's actually very nice, because what that means is that with probability that's very close to 1, when I do this test, all of these functions are actually the exact same function. They're all a dictator. And so that means that with probability probability very close to 1, all I'm doing is running my dictator test on our dictators. And we know that our dictator tests, whenever you give it dictators, the dictator test, they pass it with probability at least beta. So this will tell you that that the optimum of your instance, p, well, it's going to be at least the value of, I'll write f for this assignment that we wrote out here. And this value is going to be, well, you know, at least, like I said, at least 1 minus r times delta percent of the time you're in this very nice case. And in this very nice case, you know you succeed with probability at least beta, because you run the dictator tests on r dictators. And so this thing right here just equals beta minus big O of delta. And we're done with completeness. That's half of everything. Okay. Well, I'm kind of short on time, but we'll keep going through this. Okay, so now we're in the soundness case. We have to show that if you if someone gives you an assignment to this max CSP instance with high value, it must be the case that your unique games instance also had high value. And let me, before getting to that, let's look at, let's define something, a very nice function to define in this scenario. So if someone gives you an assignment f, f, which equals, you know, these f sub v's for all the vertices in the graph, let's define this function g sub u, which takes in Boolean inputs and outputs into the range -1, 1. And let's define it as g sub u x is just what happens when you pick a random neighbor of u and compute the value of f sub v to the pi of x, where pi is like that associated permutation on the edge from u to v. Okay. Okay, so this is actually a very nice thing to, very nice function to construct because of the following fact, which is that if you look at the value of your instance, the value that this function has on your instance, that this labeling has, it equals to the expected value over a random u of what happens when you run your function test t on g sub u. And in the interest of time, I'm actually going to skip over this, except to say that why do you expect this to be true? Well, because basically, what are you doing in this test? You pick a random u, and then you pick a random neighbor of u and use that as like the input function for a random constraint from your test t. So here again, like you're picking a neighbor, or you're picking U, and then you're averaging what test T does to all of G's neighbors. So, if you just kind of stare at it, it kind of makes sense. And basically, it would take a lot of writing out. It just uses this definition over here, what it means to test a function between -1 and 1. But yeah, so skipping over that proof. Okay, so we're in the completeness case. So in the soundness case. So in the soundness case, we're going to fix this tiny epsilon, which is at least 0. And we're going to suppose that we have an assignment that passes this test with high probability, or that passes like a randomly drawn constraint from way over there with high probability. And when I say high, I just mean actually slightly bigger than alpha and epsilon. Okay. Then what we would like to do is construct a labeling to the unique games instance, which passes with high probability. Okay, so let's think about how we might want to do this. Well, probably we're going to we're not going to start from nothing here, right? What we have right now is a labeling to our max CSP instance. So that means for every variable we also have this associated function f sub u, q. And somehow we should peer into this function and use it to suggest to us maybe what labels we should consider when assigning a label to u. And it's a function with coordinates. So one reasonable thing is just to use as your suggested labels the set of influential coordinates of this function. So I'll define that set to be the notable set, which is just the set of coordinates such that the influence of that coordinate, at least the 1 minus epsilon noisy version of it, is big. And how big? At least some epsilon over 2. The epsilon over 2 isn't so important, but it looks kind of weird. Why not just epsilon? But we need it. Okay, so one set of reasonable labels that you might use is just you take the function f of u and you take out all of its influential coordinates. But that's not just everything we should use, because this vertex u has all these neighbors, and maybe we look at neighbor v. Well, this neighbor v has it seems like v should have some say over what we label u as well, because v has there's a bijective constraint between v and u. So whatever we label f sub v with, or whatever we label v with, is going to have a strong influence over what we think we should label u with, because they're connected with a constraint. And so we should actually, in addition to using this notable set, we should also have a set of labels that correspond to what do my neighbors think I should be. Okay, and so I'll use that to define the neighbor notable set, which is basically the exact same thing. It's going to be the set of coordinates I such that the ith influence of the average of my neighbors is large, at least epsilon this time. And what do I mean by the average of my neighbors? I mean, you know, that's G function. That's the expected value over my neighbors. So I'm going to write out G sub u.
That has to be your first definition.
Yes. Thank you. Okay. And so now I'll just write my label set as the labels I'm considering is going to be the notables unioned with the neighbor notables. Okay. And basically, there are two things you need to prove about these label sets. First off, you don't want them to be too big. Because, for example, like if I used these functions to kind of suggest to me what labels I should use, then, and I use these label sets, if these label sets like contain maybe everything, then I haven't really gained any information. You know, that doesn't actually help me if it says, oh, I don't know, maybe use a label from 1 to q. And I'm like, yeah, I know that. So the first thing you might want to show is that the label set is small. And we have this old fact that if you define such a set, like this, then the size of the set is bounded, at least for this set, the size of this set is going to be bounded by like 1 over whatever this number is times this number. So neighbor notable, the size of this neighbor notable set is bounded above by 1 over epsilon squared. And similarly, the size of the notable set is bounded by 1 over this number here times this number. So, you know, it's 1 over that 2 over epsilon, or epsilon over 2. So you should get that just the notables is at most 2 over epsilon squared. So since my label set is it's a combination of these two, its size should be bounded by 1 over epsilon squared. And that's nice, because for fixed epsilon, that's a constant. Okay, now the other thing you want to show, we've gone through all the trouble of defining these sets. If it turned out they're all empty, then that's like equally bad, because in that case, the sets tell you absolutely nothing. So now we have to go through the process of showing that these sets have high value. Okay, so I'll start with a certain fact. Okay, so the certain fact is going to be that at least a certain fraction, at least a lambda epsilon fraction of my vertices have, when you have this function g sub u for them, my fact is going to be when you look at the value sub t of g sub u, when you run your dictator test on this function, sub t of g sub u, you actually get a large value plus lambda epsilon. Okay? Okay, so why is this? We're going to show by contradiction. It's because if not, then the value of your total assignment, so p of f, well, that equals, by this fact, which I didn't prove, it's just the expected value of a random u of value sub t of g of u. Okay? Now, if we're assuming for contradiction that this fact doesn't hold, then on at most lambda of epsilon fraction of these guys, do you have a large value sub t, okay? So this means that this would be at most less than or equal to. So on this lambda epsilon fraction, is this value at least at alpha plus lambda epsilon? So, you know, at most, it could be 1. And then for the other 1 minus lambda epsilon fraction, then for the rest of them, you know their value has to be at most alpha plus lambda epsilon. Okay, and so rearranging this quantity corresponds to, you get an alpha plus lambda epsilon times, you get a 1 right there, get another 1 from that, you get a minus alpha, and then a minus lambda epsilon, which is strictly less than alpha plus 2 lambda epsilon. Because you have a 2 here and you're subtracting off other stuff. And that's a contradiction. Okay? Because we assumed over here that our value was actually bigger than that. Okay. So why is that nice? Well, that means we have this large fraction of vertices U that have this property that when you run the dictator test on them, they pass with probability at least alpha plus lambda epsilon. And actually, that's not an inconsequential number. That's actually very important because we know that for these G's, these U's, we know that by the definition of my dictator test, if I pass with probability at least alpha plus lambda epsilon, we know then that that G sub U must have an epsilon notable coordinate. Okay. In particular, neighbor notables, this neighbor notable set, which is defined for each vertex to be the set of indices which are influential for G sub U, it's going to be non-empty. For a lambda epsilon fraction of guys of U. Okay. Try to wrap this up in 5 minutes maybe. Okay. So now we've shown that one of the two sets is large. Let's look at the other one. Okay, so this next claim is another fact, which is that if I'm a vertex U and I have a non-empty neighbor notable set, if neighbor notable U sub U, if I have like a coordinate I in it, then that means that's a notable coordinate for my neighbors. Okay, so in particular, that must mean that if I look at a random neighbor, then that coordinate must also be notable for that neighbor. So probability that you pick a random neighbor where I is in its notable set, so V, is going to be at least this epsilon over 2. Well, not actually I, because I is your coordinate. What you should do is like apply your permutation or bijection that corresponds to that neighbor to I. Because whenever you're shifting from one vertex to another, you should always apply a permutation. So yeah, if this neighbor notable set has something in it, then that coordinate must also be in all of your neighbors' notable sets, just kind of by definition. And this holds by another averaging argument. So similar to this one that we did over there. And basically, how would you argue? You'd say that, well, for it to be in my neighbor notable set, that means that the average of, that means that it must be an influential coordinate for like GU. But GU is just an average of, if you remember the definition, an average of my F sub U, or F sub V's for my neighbor V's. So if that average is large, then it must be large for actually a lot of them. Okay, so I'll just put this together now. And so if you think of a random edge, U to V, you just pick U randomly and a random neighbor, then you know first off that neighbor notable is non-empty with probability lambda epsilon is non-empty. So with probability lambda epsilon. And then if neighbor notable is non-empty, so it has this coordinate I in it, then you know, conditioned on that, with probability at least epsilon over 2, your neighbor's notable set is also non-empty. So just notable sub u is non-empty. So this event happens with probability that's basically like big theta of lambda epsilon times epsilon, which is nice. Okay, so now, and furthermore, like by the other fact I proved, these sets are actually small. So you know, for a large percentage of the edges, the two sets are are non-empty, but they're still small. Okay, so let's finish this then. Our whole goal was to make an assignment to the unique games instance. So instead of making an assignment, I'm going to make a randomized assignment. L for G. And I'm just going to set L of U. I'm going to say, what label should I assign to U? It's just going to be uniformly random element of from the label set. Okay. So what is the value of this randomized assignment and expectation? The expected value of the randomized assignment is, well, let's throw out all the edges where this event doesn't happen. Okay, so let's just ignore them. But we still know that with probability at least lambda epsilon, or big O of lambda epsilon times epsilon, we know we fall into the case where you have like one vertex has a non-empty neighbor notable set, the other one has a non-empty notable set, and like there's a matching label in the two. So this is times, okay, so when you're in that set, now you just have to make sure that when you randomly pick a label from the two sets, you get the two matching elements. And so we want the probability that this permutation, the bijection, applied to L sub v, this is just the success probability condition on this case, equals L sub u, conditioned on u and v are, let's just call that the good event, okay? Okay, so yeah, finishing this up, if they're good, like I said, they have a matching label, and their sets are also small. Both of them are at most size 1 over epsilon squared. So the probability for L of v that I get like the label I'm looking for is going to be at most, or at least, this is going to be at least 1 over the size of the set, which is 1 over epsilon squared. And then the probability for u that I get the label I want is also 1 over the size of the set, which is 1 over epsilon squared. So this quantity right here is at least epsilon to the 4th. The whole thing is at least lambda epsilon times epsilon to the 5th. And you know, you should throw big O's around everything, or big thetas. Okay, so what this actually says then is that we have a randomized assignment with a large value, but you know, by the probabilistic method, that gives you an assignment with a value that's at least this. And that completes the proof just because this just shows us if on our max CSP instance F, we have a large value, that immediately translates into a large value for